Alright, so we're going to take a look at a different problem this time. And we're continuing working with forces. It's called dynamics. And this one is going to be another story type problem. This one is related to something that I did a couple of weeks ago. My sister bought a play place type thing for my nephew from, I think it used to be at a church of some kind, but it looks like one of those ones where it's a play place like inside a fast food restaurant. And the thing's gigantic. It's just gigantic. There's a full thing where it goes like 2 or almost 3 stories tall, and there are a bunch of wires and then, or not wires, but pipes that help support tubes that they can crawl around in. It's basically like a giant hamster wheel thing for children. I assume that's more or less what they were going for. Anyway, part of it was a little house type thing that one of the tubes would actually let you get into, and it had little windows and all of that, where it was kind of like a clubhouse. My sister liked to call it the Pink Palace, because it was a pinkish color on the plastic. I'm not certain my nephew will be entirely stoked about that, but my sister intends to paint it green, which I think he will enjoy. So, anyway, we had to go pick up this monstrosity, and we had to attach it to a trailer and then drive it a long distance, and there was much lamenting and gnashing of teeth, if I recall correctly. But first we had to push it over towards the trailer itself so that we could then lift it up and put it on there. So what I'm going to do is we're going to take a look at a problem where we find out how much I probably had to push on it to get it close to the trailer. Okay, so I estimate that the mass of the Pink Palace is something around 25 kilograms. And when I was pushing it over the grass, I expect that the coefficient of kinetic friction, of sliding friction, is going to be something like 0.5. It was kind of rough, but it wasn't incredibly rough, and so that's a pretty good value. So let's get an idea of how much force I have to apply. So my normal force, my force of push, how much I have to push onto this guy. In fact, let me, just so we don't get it confused with the other, we know it's a type of normal force, but we're going to call it force sub P, of me pushing or pulling this monstrosity. Okay, so that's what we want to know. I want to know exactly how much effort I had to put forth, because those are probably billable hours if I start thinking about it. And I want to find that out. Let's say that I'm just pushing it, I'm not making it speed up or anything, I'm pushing it at a constant velocity. So constant velocity. Now I will often describe things as constant velocity, and many people who deal with physics problems will often say constant velocity. What does that mean? Well, that's a specific phrase you want to keep an eye out for, because constant velocity means it's going the same speed, the same velocity at all points. So is it speeding up or slowing down? No. And if it's not speeding up or slowing down, this phrase basically translates into our acceleration is equal to 0. And that's pretty useful information for us. So keep an eye out for this phrase, constant velocity. Okay? Alright. So I'm going to push this at a constant velocity. Its mass is about 25 kilograms. The coefficient of friction between it and the ground to push it over to the trailer to transport it was 0.5. And I want to know how hard I was pushing it. Okay, well, we've got a drawing. I will add me in, pushing it. Sad face. And sweat, because I assume I pushed it really, really hard. We'll find out though. Maybe I'm just out of shape, horribly, horribly out of shape. Okay, so we've got our drawing. Now we want to declare a coordinate system. We'll do up as the plus y, and to the right as plus x. Stick with what we know. I don't see any good reason for us not to. Alright, so now I've got a picture. I know what directions are what. I'm probably dealing with forces because I want to find out how hard I'm pushing this horrible, horrible thing. So, the best way to keep track of forces is going to be to draw a free body diagram. Okay? Well, I'm going to draw a free body diagram of the pink palace. Well, it turns out that we picked it up very near the surface of the Earth, so gravity was pulling down on it. That's mg, our force of gravity, near the surface of the Earth. It was on the ground and not falling down into some sort of hole or sinking down into it, so the ground was providing a normal force to help hold it up. I am going to apply a force onto it. I'm going to try and push it in the positive x direction here, because that's the thing I want to find. Pardon me. And in this case, we're saying you've been given a coefficient of kinetic friction, so there's a very good bet that friction is involved in this. Okay? So we've got a frictional force. Well, if I'm pushing it to the right at some constant velocity, then friction, which has a tendency to oppose motion, is probably going to try and slow me down, fight against me. We're going to have our force of kinetic friction pointed back off to the left. Okay, so we've got a good number of forces this time. 2 of them happening in the y direction, 2 of them happening in the x direction. Alright, well I've got to apply something. Now that I see these forces, I've got to be able to do something with them mathematically. There's some sort of law relating forces and motion, because I'm dealing with how much it's moving. Which law? I think it was a second of some kind. It's Newton's second law. Okay, so we had sum of forces equals mass times acceleration. But remember, our force and our acceleration are vectors. Well, that's okay. We've added vectors before. You can check the videos if need be. So vectors have direction and magnitude. We can't just add the magnitudes together because that totally ignores direction. But what we can do, just like we did in all of the vector videos, is we can split those vectors into their components, what's happening in the x and what's happening in the y. That's why we have these 2 coordinate systems. Okay? Well, I'm going to do sum of forces in the x equals my mass times my acceleration in the x. Sum of forces in the y equals my mass times my acceleration in the y. Okay? Well, let's take a look at the x direction. My sum of forces in the x, I'm going to say that even though, yes, it equals my mass times my acceleration in the x, my sum of forces in the x also is me just adding up my forces in the x, and I totally pointed at the y direction there. So here in the x direction, which we're actually looking at, what have we got? Well, we've got a positive force from me pushing on it, and then pointed off in the negative direction, we have the force of kinetic friction, kind of fighting against me. All right? And then in the y direction, I've got my normal force, like usual, minus my gravitational force. Also pretty usual. All right. Well, in the y direction, what's my acceleration in the y? The pink palace did not fall off of a cliff as much as that would really have made my day. It didn't jump up off the ground, or the trailer for that matter, which was good, because that wouldn't have made my day. So our acceleration in the y direction is 0. Okay? 0 meters per second squared. What about the x direction? Well, I told you that I'm pushing it at a constant velocity, and we saw up here that that means that our acceleration is equal to 0 meters per second squared. I'm not speeding up in the x direction, so I'm going to do 0 meters per second squared. Alright, so taking these guys back up here, hopefully where we can see them, I've got 0 equals force of push minus my force of friction. Well, let's take a look at that real quick. I can add my force of friction to both sides, kinetic friction, and I find that my kinetic friction is equal to my pushing force. Okay, well I want to find my pushing force, so if I can find my force of friction, then I'm in good shape. Alright, let's take a look at our notes. What's the equation for the force of friction? Kinetic friction, to be precise. Well, we know that in general, our force of kinetic friction equals our coefficient of friction times our normal force. Well, I know my coefficient of friction, it's right over here, 0.5. But I don't know my normal force right offhand. Luckily, I thought in advance and went ahead for the practice and solved or put in information for my sum of forces in the y direction. And that is where my normal force shows up. Taking this guy up here, we also have 0 equals my normal force minus gravity. I can add the force of gravity to both sides. And I end up with force of gravity equals my normal force. Cool. I know my mass, it's 25 kilograms. I know gravity, the acceleration due to gravity, little g, which is 9.81 meters per second squared. So now I know my normal force. I can plug it in up here, and I find that my force of friction, sliding friction here, is mu sub k mg. Okay, and I know from up here that that is also equal to my force of push. So I just plug these in and I'm set. So 0.5, that's my coefficient of kinetic friction. My mass was 25 kilograms, and g is 9.81 meters per second squared. I carry all of those through, and I end up with the force that I'm pushing with equals, if I've done this correctly, what is that? That should come up to about 123 newtons. Well, that's not too bad. Moving that over to pounds, just off the top of my head, is going to be something like 30 pounds or so. Let me double check. So if I've got 123 and I divide it by about 4.4, about 30 pounds. So, wasn't nearly as bad as I thought it was. Okay, I just remember it being much worse. And the Pink Palace successfully made it over to my sister's house, and so, oh no, that reminds me, I'm probably going to have to go help her build that again soon. Alright,